Morning, students. Today we shall discuss amplifier models, right? I think it's the next part in your syllabus. There are different types of amplifiers, and another point I want to remind you: do not think that an amplifier essentially amplifies a signal. There are various electronic circuits which have an input side and an output side. And in general, they're all called amplifiers. And the particular amplifier that we use for amplifying a signal, we call them signal amplifiers. Anyway, here we shall have a short lesson, and actually, it will give you some basic concepts, not design principles, etc. So there are few types of amplifier models. We shall see here the four basic types. First type is a voltage amplifier. We call it a voltage amplifier. And it looks like this is a schematic diagram, or you can say equivalent diagram of a voltage amplifier. The part in this yellow box is the amplifier. This is a equivalent circuit. Inside there may be a lot of electronic components, but equivalent is like this. This voltage amplifier, any such equipment or any such electronic circuits will have an input impedance. This is the input impedance. In fact, this is a Thevenin equivalent of a voltage amplifier. Input impedance of the voltage amplifier. Whenever you try to give any input signal, it will obviously face the impedance or resistance. That is the input resistance, which we name Ri. Okay? And Thevenin equivalent of a voltage amplifier, since it will give voltage output, there is a voltage source here. And Thevenin equivalent calls for a resistance in series of the voltage source. This resistance is normally a very small resistance. I think in your school, you have learned the source resistance of a battery, right? It is that resistance. It will always have a resistance, however small it may be, and it is normally small. So, Thevenin equivalent of a voltage amplifier, there is an input resistance or impedance, there is an output resistance or impedance, and there is a voltage source. And the value of this voltage here is the input voltage Vi, which comes to the input, multiplied by a factor of AV. And AV is called the voltage amplification factor, or simply amplification factor. Or normally we call it gain, voltage gain. AV is the voltage gain. So I think I could explain to you the Thevenin equivalent of a voltage amplifier. I repeat once again, there is the input resistance, there is the output resistance in series with the source, and the output voltage is AV times input voltage. Okay? Now, purpose of this voltage amplifier is, keep in mind very clearly, purpose of this, its voltage output should be proportional to voltage input. This is the purpose. That means here, this is the input Vi, which is falling into the circuit, but for you, the voltage input is Vs, the source. For you, voltage input is a source, and the source also has a resistance in series. This is the property of any voltage source. And this series resistance of these voltage sources are normally very, very small. Okay. And at the output, this is your load, RL. The load is normally another equipment, but we always represent it by a resistance RL. In fact, this is the input resistance of that load, right? And a voltage VO appears across the load. The purpose of this is voltage output, that means VO must be proportional to Vs. Irrespective of this RS, RI, RO, RL, etc., VO should be proportional to VS. That is the purpose. That purpose, how do we achieve that purpose? One basic law: source resistance RS must be much smaller than input resistance of the voltage amplifier. This is number one. And number two is the output resistance of the amplifier, rather source resistance of the amplifier must be much, much smaller than the load resistance. These are the two basic requirements. Now, if you can design a circuit like this, right? If you can design a circuit like this, then you see here the VI, what is the value of VI? You can calculate is VI is this voltage VS divided by RS plus RI, RS plus RI, that multiplied by RI. I think you have no problem in understanding this, because VS, this VS divided by RS plus RI makes the current in this line, and that current multiplied by RI is the voltage here, VI, right? Now, this condition is here, RS is much, much smaller than RI. So if RS is much, much smaller than RI, then this RS plus RI is almost equal to RI. And this RI and the numerator RI gets cancelled, so VI becomes almost equal to VS, right? In that case, voltage created by the amplifier, AVVI, is equal to AVVS, because Vs is almost equal to Vi. So AVVI is equal to AVVS. Then, what is the value of VO? VO is this voltage AVVS divided by RO plus RL, and that multiplied by RL here. Once again, RO is much smaller than RL. If RO is much smaller than RL, then this factor gets almost equal to 1. So this becomes equal to AVVS. So what we get? VO is equal to AVVS. That means VO is proportional to VS. This kind of a technique where source resistance is much smaller than the input resistance of the amplifier, and load resistance is much bigger than the output resistance of the amplifier, it works as a voltage amplifier, where voltage output is proportional to voltage input. Okay. Now let's go to the next type. Next type is a current amplifier. Current amplifier purpose is current output is proportional to current input. Inside this yellow box will be a complete different design than the voltage amplifier, but this is the Norton's equivalent of a current amplifier. Norton's equivalent of a current amplifier, once again, there will be input resistance, and there is a current source inside. There is a current source inside here, and the value of the current produced by this source is AI multiplied by II. What is II? II is the current that flows through the input resistance, and AI is a scalar. AI is normally called the current gain, right? And Norton's equivalent, there is a resistance in parallel to this current source. These things I think you have learned in your first year, that for Thevenin equivalent, a voltage source has a resistance in series, and in Norton equivalent, current source has a resistance in parallel. And this is the output load as usual. Here, this is the current input because the purpose is to amplify the current. Here it was a voltage source. Here it is a current source. And once again, a current source will have a resistance in parallel to this. This is a Norton equivalent of a current source. Now, how does this work? Here, Ri must be much, much less than Rs. Here, Ri was much bigger than Rs. Here, Ri is much smaller than Rs. Right? Also, load resistance must be much smaller than Ro. If you can calculate these values properly and design an amplifier, then what do you get? Firstly, let us find out what is II. Because this value is II. So we have to find out II. Now here is a source current Is. This current goes into two branches. One branch is Rs, another branch is Ri. So if there are two parallel branches, I think you have done it in your school also. Nowadays, they teach it in school. And if not school, you have definitely learned in your first year that this current, when divided by in two parallel line, then current in this line Ri is given by source current Is multiplied by Rs, the other branch resistance, divided by sum of these two resistances, Ri plus Rs. Now we have seen here condition of the design is Ri is much smaller than Rs. So if we ignore Ri, then this factor becomes almost equal to 1. So II becomes almost equal to Is. In that case, this current AIII is equal to AIIS. Then, if this is AIIS and then again dividing into two branches, then what is the load current? IL is equal to basic current, original current AIIS that multiplied by other branch R0 divided by the sum of two branches R0 plus RL. Once again, R0 is much smaller, much bigger than RL. So this RL gets ignored. So this factor becomes almost equal to 1. So this becomes equal to AI equal to IS. So what do we get? Load current IL is proportional to source current Is. So this was the purpose of this amplifier. The current output should be proportional to the current input. And this is the basic condition of this design. The design itself, you will learn it later on if it is in your syllabus. Now let's go to the third type. Third type is a transconductance amplifier. This name is very threatening name, but actual application is very common. Here, current output is proportional to voltage input. Here, the input is a voltage source and output is a current. In our electronic circuits, we often need this particular electronic circuit where current output is proportional to voltage input. And in fact, do you know what it is normally called? Commercially, it is called voltage to current converter. This transconductance amplifier only it is there in your textbook. It is called voltage to current converter. That means this is a voltage input, current output. Voltage to current converter. And its condition is this source resistance RL of the voltage source must be Rs of the voltage source must be much smaller than Ri. And here the load resistance RL must be much smaller than Ro. Ro is the Norton equivalent of this current source. If you design an amplifier as a current source, there will appear impedance in parallel to the current, and that is R0, right? And value of this output current source is normally designated by GMVI. GM is the transconductance gain or voltage to current gain, and VI is the voltage that appears at the input terminal of the amplifier. And the calculation is exactly similar. What is VI? VI is Vs divided by Rs plus Ri multiplied by Ri. And since Rs is very small with respect to Ri, so Rs gets ignored. This becomes almost equal to Vs. So, and this current source is GMVI. So, GMVI is practically equal to GMVS. That is the source voltage, GMVS. And then next part is also similar. Output current IL, if this is the current which is GMVS, this current is GMVS, then output current IL will be GMVS multiplied by RO divided by RO plus RL. Once again, this factor is almost equal to unity. It is GMVS. So what do we get? Output current IL is proportional to source voltage Vs. That was the purpose of this amplifier, and it is called transconductance amplifier, right? The fourth type that is mentioned in your syllabus is transresistance amplifier. Transresistance amplifier is actually current to voltage converter. This was voltage to current converter, and this is current to voltage converter. These based amplifiers or electronic circuits, current to voltage converter and voltage to current converter, they are very often used in various instrumentation. Various medical instrument or any instrument, they are used very commonly. This is transresistance amplifier, where output voltage is proportional to input current, source current. Condition is this input resistance of the amplifier Ri will be much smaller than source resistance Rs. And here, this RL load resistance must be much bigger than RO. If you can design accordingly, then once again, and this is the value of this voltage is RMRI. RM is the transresistance gain, or we can call it current to voltage gain, right? RMII. II is the current which flows into the circuit. Mind it, IS is the current of the source, but II is the current that flows into the circuit. This II is equal to, by the basic formula, source resistance IS multiplied by Rs divided by Rs plus Ri. Once again, since Ri is very small with respect to Rs, Ri is ignored. This factor becomes almost infinite. So II is almost equal to Is. And this voltage is RMII. So RMII almost equal to RMIS. This is the voltage value, right? Now going to the next, if this voltage is RMIS, then what is the output voltage? Output voltage is RMIS divided by RO plus RL and whole multiplied by RL. Once again, since RO is very small with respect to RL, this factor becomes almost infinity, and this becomes almost equal to RMIS. So what do you get? Output voltage is practically proportional to source current. So this is a current to voltage converter. This is a voltage to current converter. Earlier two were voltage to voltage converter, but we call it voltage amplifier, and current to current converter, but we call it current amplifier. These are the four various amplifier models. Okay.